well as on extracting data from customers, cleaning it, and ensuring that we are delivering what they actually want, which is honestly much harder than developing a good model. So today I will talk to you about XGBoost, an algorithm that is used in vast majority of winning solutions to machine learning competitions. And how these competitions look like? These competitions are about this cherry on the cake. So simply, you create models. The data is already provided to you, and on the one hand you have a train set on which you have all the features and a certain target, which can be a classification or regression problem. On the other hand, you have a test, and your task is to, using the training, predict what is going to be on the test. And each of such competition has a certain measure of success, and you compete with other people. So there are plenty of pages on which you can take part in such competitions, but there is only one true king, and it's Kaggle. So it's not only a site with competitions, it's a true data science community. It hosts a lot of competitions. Even now you can find for free competitions that are still running, and there was a time during this year when there was around 7. And each of them are very interesting, and you can really learn a lot. So these are the competitions, but the community there is all about learning and getting better in data science. So people help each other to understand how things work. And for example, a person that developed XGBoost, this winning algorithm, shared it with everyone else. It's an open source algorithm, it's for free, and many people are working to make it better every day. So we will focus today on 3 competitions that were quite popular. It was a classification of products for Otto Group, a very large company that is actually an umbrella organization for other companies in Germany. I think everyone knows Rossmann. And also there is a Russian company called Avito, and they have a business related to online advertisements, and they wanted to predict click-through rate. So now some details about these 3 competitions that I have chosen. In Otto, you had 93 features, and the meaning of the features was not disclosed. So when the features are not disclosed, it means that they can be anything. And there are different reasons for not disclosing the features. For example, if Otto really wanted to have a good model for classifying the products, features are part of this model, and it's their intellectual property, and sharing with everyone what exactly was done, plus the models on Kaggle are very often quite public, even the code of the models. So they would have actually nothing from it but an advertisement that they do data science. So sometimes they really want to use that models, and having these anonymous features or not everything described how was created and collected can be a part of their business process. So simply, every product is described by 93 features. We have 9 categories. We have this training set, test set, use test set to predict the probabilities of the categories. That's it. For click-through ratio, on the other hand, we actually gave an SQLite database with a schema like this, and it was your task to create all the features. So it was really also nice in another way, because you could focus on creating the features by yourself. So you could use some creativity, not only your intuition of using the right model, but also what actually to put in the features. And in my opinion, the best competition that I know on Kaggle was Rossmann, because it was. So I also work in predicting sales for certain stores, and Rossmann sales competition was very, very close to the data, and of course it was not so detailed as, for example, we have in our commercial model, but they really made, the data made sense. It was the sales of each of the stores that Rossmann has in Germany for each day. And also for each day you had an information, whether it was a holiday, a school holiday, or a normal holiday. For example, it allowed you to not to focus on knowing that in Germany, in different lands, holidays are in different seasons. So it also encouraged a lot of creativity, and the contest was mostly about engineering the right features rather than just testing a lot of models. As I mentioned, in such competitions, the best solution wins. But what is the best solution? It always depends, yes? For Rossmann, they wanted to minimize the percentage of the error. So instead of a standard regression measure, so how good regression is, normally you have an average of squared differences between your prediction and what actually was there, and of course you take the root from it. So it's called L2 norm. They had L2 norm, but not from raw predictions, but from percentage. So percentage was more important for them. As for classification, so the most popular measure that is used worldwide in anything is accuracy. So what is the percentage of things that you classify correctly? You will not find something like that in Kaggle, because actually you always want to know how good the model is and how certain about the prediction it is. So always the output will, the measure will actually be related to the probabilities that you have given. And if you are sure, so here is the loss function, the example binary loss function for Avito, and the ad was clicked here, and you gave a certain probability that it was clicked. So if you were really sure that it was clicked, your penalty was really small. But if your model was just, well, I have no idea, half by half, then the penalty was around 1. But if you stated that I am really sure that this ad will not be clicked at all, your error normally could go to infinity, but it is capped at around 35. So this measure ensures that you don't provide any extreme solutions, that when your classifier is wrong, it should be wrong only by certain margin. So it should not only be wrong, but tell, okay, I don't know. I think it's that, but who knows? And very similar measure is used for this auto group classification, but it's converted to work well for multiple classes. So I told you about the problems. Now, what actually do we use to solve these problems? And the most known family of classifiers nowadays are decision trees. Random forest that is so popular consists of decision trees. Decision trees themselves are quite, if they are not too large, they are easily explainable to someone, like, okay, if it's bigger than that and smaller than that, then probably this will be clicked or something like that. But, well, we have more and more computer power with every year, and decision trees were developed a couple dozens of years ago, I believe. So now we can have multiple decision trees, like we had a committee of experts, because when you have an error on a tree, the error can come from two sources. So the tree can be too specific about a certain particular situation that occurred, and then it means that it's not doesn't generalize. So you will have the predictions that vary, or you can have a tree that is biased, and it will simply tell you all the time that it's wrong, but it's consistently wrong in the same point. So the classic example for decision trees dataset is the question, shall we play tennis? Imagine that you are an English lord, you have a butler, because you are too lazy to look outside yourself, yeah? And the butler should make a decision himself. So John, is it a good weather to play tennis today? Yes, sir, of course. So, well, times have changed, butlers are expensive. We can replace John with decision tree. But the question is how to create an accurate decision tree. And there are many different algorithms. There are algorithms based on entropy with information gain, with gain ratio, with Gini index. A lot of different stuff that I'm not going to go into, but their work is always the same. To create the tree that would classify the instances correctly in general, but would not be too specific about certain situation. So once again, I will go to the sources of errors in trees. With another illustration. So our perfect situation is that we have just the right tree. It generalizes well and it is consistent. So imagine that in statistics you always have some population and then you take some sample to investigate. So John wouldn't see all possible weather conditions that there were, but imagine that we have a lot of butlers, yes, and each of them would have their own hunch what would be a good way to play tennis, or when is the good weather. And if they had low bias and low variance, then it means that every time when the weather was appropriate for this particular example, every time each butler, in some situation, each butler would tell you that yes, it's good weather to play tennis. If you had a high variance but low bias, then each butler would tell you different thing. But if you would ask all the butlers and just take the majority vote, then it would be right. So a committee of butlers would tell you whether it's good weather to play tennis. But your butlers could be biased. For example, they really don't like cold weather and you're not bothered by it. But they all don't like cold weather, and this particular example would be with cold weather. So they all tell you, no, it's not good weather to play tennis. No. So then you have a bias. And of course, worst possible situation, you have high variance, high bias, so they tell total bullshit. And there are several methods to reduce, in any classifier, not only in decision trees, to reduce the errors that are coming from variance and to reduce the errors that are coming from bias. So, for variance it is quite straightforward. I have told you that if you had a lot of different classifiers, like the same model but trained on different samples actually, then an average prediction would be good, would be fine. And that's the idea of bugging, the bootstrap aggregation. It was invented by Leo Breiman around 20 years ago. And simply you have some training set with 100 examples and you want to train, let's say, 100 models. The more the better, because it reduces variance, not the bias, so you cannot overfit here. So the the bigger it all depends on your time and computation power. So you simply use a random choice for every observation that is here, and create first row, second row, third row. As you see, some things can be chosen multiple times, and some things are not chosen at all. The general probability for this is around 66%, that at least one instance of something would end up in your example data. And then you train your model on this resampled data. And suddenly you now have this committee of experts and you can reduce the variance. But the thing is that there are some features that, for example, we have 1,000 examples and only 3 categories. So even if you resample it, the distribution will be similar. And if this particular feature would be the cause of your error, the bugging would not help you. So Leo Breiman, some couple of years ago, that's the same guy, came up with another idea. So let's decorrelate the models. Let's make them different errors on different uncorrelated errors on different rounds of bugging. And I just had to put some image here. So random forest is simply bugging with decision trees for which the columns, the attributes that you can choose from are randomly chosen at each point of split. And it causes the decorrelation of error and further reduction in variance. So random forests are another type of algorithm that you cannot overfit. So the more trees in random forest you have, the better. It will never be overfitted. But as I said, the variance is only one part of errors. And another part is coming from bias. We also would like to have this part of error reduced. And bias in resampling will never be, the bias error will never be reduced because it's the limitation of the very algorithm that you are using. So there are simply some situations that decision tree will not be able to model at all. And let's take a look at the example of a very simple decision tree. You have just one node, and you can either split the examples vertically or horizontally. So as you see, there is no way that with one tree you create a perfect classifier here. And if you resample, then an average classifier will also make the same errors, yes? Because on average they will compensate each lack. So it would require lack to have only the examples that are possible to separate drawn from the sample. So any lack on that side will be compensated on the other. So with bugging you will not be able to do this. And Robert Shapiro came up with another idea, and it's called adaptive boosting. So simply, when your algorithm does wrong on certain examples, let's reweight the examples. And now it will focus on those three examples. And although the rest of the examples will have a decreased weight, those will have increased weight. So it will focus on errors. And here with just 3 rounds, we have our perfect classifier, despite the fact that the basic one that we have used would not be able to model, to create the good model for this. But adaptive boosting has a problem with observations that would be constantly classified wrong. Because our world is never perfect, and simply sometimes you have examples that are pure noise. There shouldn't be there. So probably someone made a mistake and classified them wrong. And now your adaptive boosting would focus to classify it right, thing that is not given right. And it would overfit. It would create the model too specific for not what is the actual hypothesis. So another boosting idea came up with by Freund. It's called gradient boosting. And actually XGBoost stands for gradient boosting, but it's the combination, a little bit combination of gradient boosting, bugging, and random forest. So with gradient boosting, comes up with an idea of improving the existing prediction. So we have some prediction, and we want to add a new model. So it's fixed. This is our prediction. Now we want to add something to fix the errors. So what we are actually predicting now for the problem of regressions are errors in certain examples that are called residuals. So residuals in the regression are the individual differences for each example between what it actually should be and what our model says it is. And a very well-known regression model is between your height squared and weight. It's called body mass index. And it's supposed to tell you what is the perfect weight for individual of certain height. But some community of experts created their own model, not a mathematical one, but let's say an empirical one. And these were the exact differences that were between this BMI model and this one. So imagine that we want to fix BMI. So we take it as our initial model, and then we concentrate to fix the errors. And then after fixing these errors, we do it again, and again, and again, and again. Oh, sorry, just one more thing. Why is it called? Because we are focusing on residual. And it's called gradient boosting, not residual boosting. So the reason is that, as I told you, the main, the classic loss function for regression, so the penalty that you have, is squared loss function. So the sum of squared residuals, and then the average of them that is under the square root, is the actual number that describes how good your model is. So for each of the examples, the contribution to the error is equal to squared residual. And it happens that the gradient, so the first derivative, over the prediction function of the squared residual is 2 times residual. So they normally do this math trick that they multiply it by half to make it nice and clean. And that's why it's called gradient boosting, because mathematicians always like to generalize. So there was an idea, intuitive one, on regression. On classification, it will not be that intuitive, but it generalizes really well and simply works in a similar manner. Just a different loss function is applied. So now I found in Google Images some nice function that is very, very complicated, has a lot of local minima and maxima, and you are in some point here. So your prediction is at some point, and your expected value is at some point, and imagine that we are crazy enough to use this as our loss function. And we want to minimize the loss. So when you would calculate the gradient and take it with the negative value, it would tell you what is the steepest way down. So I want to go down. I want to minimize my error. That's the gradient here. So to sum up how gradient boosting works, you start with some model. I gave you an example of BMI, but normally it would be something really simple. So as a standard for classification problem, it would be a uniform probability. For regression, it would be just the mean of all the values. And then you start your iterations of predicting the errors and compensating for them. However, if we go back for a moment to these nice mountains, well, if you are near the top of the mountain and you jump a little bit too high, you will not end up in this lovely valley, but you will jump to another mountain. So these models are aggregated with a parameter called shrinkage. So you want to take a smaller step. You use the gradient to point you the direction, but then you just say, okay, let's look again. Where should I go? Yeah? Not to miss the place you're looking for, which is your minimum. So, having all this background to XGBoost covered, let's talk about this algorithm. So XGBoost stands for Extreme Gradient Boosting, and it's a little bit custom implementation of the algorithm that I just have shown you, because it has a specific way to grow trees. So I told you that trees can be used with using the information gain, or gain ratio, or Gini index. XGBoost uses neither, because its author really likes the neat mathematics. So the objective is purely numeric, and it strictly relates to the function that you want to minimize. So it can be used for classification, it can be used for regression, it can be used for ranking, and you can even create your custom last functions for it to be optimized. It has interfaces for R and for Python. Well, actually there were times that for R was quite better one, because I think it still has better done analysis of feature importance that are used in the model. But still the Python one is easier to use and neater in my opinion. And it can also be executed directly via command line or on Hadoop via Yarn, which is the resource negotiator for Hadoop. So how it handles the data, it's quite important, because it handles only numeric data. Only that. So it is your task. It's not as simple as some stuff from Dato. You need to prepare the data set yourself, and it has to be all numbers. But it's not that hard task, to be honest, to doing it in only having a numeric values. And for example, in this tree that I have presented to you, the categorical features were split in 3. So XGBoost always makes binary split, because it's fast to find the binary split of numerical feature. So it simply takes all the features, finds the best point of split, and then splits again on the lower level. As for nominal values, if you ever worked with, I don't know, neural networks or other algorithms that also do not accept the features that are nominal, you know that there are ways to encode them, and the easiest one is called Hot Encoding or dummy encoding, where simply for each of the categories you put 0 or 1. And for some neural networks or linear or logistic regression, normally you would, when you do Hot Encoding, you need to delete last feature, because they have linear code dependencies, and it can break your model. So in XGBoost, actually you need to have all the features, because they should be, each of the features should be possible to model with one split. So you need to do that. And any transformations that are done in other models for XGBoost do not matter, because it sorts the values according to to the feature, and then it searches for a split. So if you normalize it, if you standardize it, if you take the square root, the logarithm, whatever transformations that you would normally seek in other algorithms, it will work almost the same. And this almost is only related to the fact that if you have a split between 4 and 5, the split point will be 4.5. So of course, if it is transformed somehow, it will be a little bit different. But when you want to have a good model, you never do the transformations that are monotonic. And last but not least is handling the missing values. So in scikit-learn, when you go to the page that says about missing values, it shows you how can you do the missing value imputations, because, let me paraphrase, well, not all the data is given. So in my opinion, I have never seen the data set that all the data was given. So it was quite obvious that not all the data is given. And what is more, it is very often that your data is not missing because someone forgot to place it there. It's missing, and the fact that it's missing is because, for example, in a form there is a surname when you were a maiden and you never were a maiden. So it's not missing because someone forgot to fill it in. And that's a very common case. So XGBoost in each split handles such values separately and put them in one or another branch depending on how the function that it optimizes chooses. So it minimizes some objective and simply in each split it decides where missing values would go. And I believe that it is one of the reasons that it almost always outperforms the implementation in scikit-learn. So by the way, the same author that is the author of XGBoost is an author of gradient boosting machines in Data. I'm not sure whether it's exactly the same. I assume that not. I don't know Data at all, actually. So, but I just know that he did the implementation. So. Loss functions. So it's something that is very important for Kaggle. Not so much in your real life work, but in Kaggle you really are struggling to have the fourth digit after a comma a little bit lower than someone else. You would never do this in normal life because you simply don't have time for it, and when the model is good enough, it's good enough, and it doesn't matter that you spend just 48 hours to go 0.003 below the previous one. But in Kaggle you do. And sometimes the differences between first and second place are really like a statistical error. So, as I told you, almost in many cases, quite often, the evaluation metrics on Kaggle are standard ones, and the exact three ones that are in the first part of the slide here. But sometimes not. For example, for Rossmann, it was percentage error, not the normal error, and also for regression tasks, you almost in every case when you predict something that is similar in nature to sales, you do the logarithmic transform. And suddenly, your loss is a little bit different. So actually, someone in Kaggle with good math skills proved that after this logarithmic transform, the percentage error and this normal error have a very similar way of working in XGBoost. But if they didn't, you could implement, if it was differentiable at the single example level. So for example, sometimes the measure is area under curve, under receiver operator curve, and to calculate that curve, you need all predictions and all example, and there is no such thing as a contribution of single example to the curve. it doesn't work like that, because it's based on ranking. So in such case, you cannot write your objective that would maximize the area under curve. But if you have logistic loss, or for some, I believe, Higgs boson searching, there was some totally custom objective related to physics, you could, it was differentiable on the level of single example, you could write your own loss function and actually optimize it with XGBoost. And it's not hard, because XGBoost doesn't use the exact function, but the Taylor series approximation of the function of the second degree. So it just uses the gradient and the Hessian of the function. So it's so cool, I guess, that you would like to try it out. And you have the opportunity to do so. So some time ago, Kaggle introduced Kaggle scripts. You can just log into Kaggle, go to some competition, run script, and just code in your web browser all the libraries that are used by many people. The so-called Python data science stack will be there for you. But you can also replicate this on your local machine when you don't have a time limit for a model, and when it's much faster, because on Kaggle it just has a function of a toy to play with. If you really want to create a good model, you need to do it on your own machine. And if you'd like to have everything set up for you and avoid all the pain that is associated to setting up by yourself, you can use Docker Kaggle image that is a Docker virtual machine. And it really well works on Linux. On Windows, it works, well, okay. But on Linux, it works really well. You can also just install the Python package for XGBoost on Windows with MinGW compiler, because it is all written in C++, with some library that I do not recall now that helps with parallelization. So you need to compile it yourself, because it's somehow related to the architecture that you have on your PC. Or you can use Visual Studio, but recently they abandoned it, and you would need to go to this revision, download the old version of XGBoost, and you can compile it with Visual Studio. But still you would need to download the whole big Visual Studio just to compile XGBoost, so I still would stick with Docker. So now some code example. As I have mentioned to you about Autodata, we have 93 features that we have no idea what they are. We have a class. We have a test set that doesn't have a class, the target, and we need to predict this target. And in every competition, Kaggle gives you something that is a sample submission. It usually scores really poorly, because it's something, for example, here, it simply says that with 100% sure that everything belongs to class 1, which I doubt, so it would not be a good solution, but it's a nice template. Then you can put your prediction just into it, save to CSV, and upload to Kaggle. So now some code example. So I will just tell a few things. First, we used Pandas. That is a free version of S-Frame. And it's really, really good. I really recommend it. But it is true that it works only in RAM. So if you have the data set that is too large to fit in RAM, the Pandas will not handle it well. So now, this actually is the code. I give you the link at the bottom. That is the link to the Kaggle scripts. So you can go there, see the code yourself, and then you can fork it, play with it, and just without installing anything, see how it can be altered, changed, or whatever. So, in this competition, all the features are numeric. so we do not have to do any transforms. But in pandas, it's really simple. You just use get dummies, and you have dummies for categorical variables. So it's not hard to do, but I just wanted to keep it simple and about XGBoost, not about the rest of Python data science stack. So then there is some convention in scikit-learn. You use capital X to define the feature matrix and small y to define a target vector. It needs to be vector, one-dimensional. That's why I use the Ravel function there. And then you can use XGBoost either directly via Python API, or it has also an object that is compatible with scikit-learn. So on this example, I'm using it directly, and there was a time that it had a big advantage, because the one that was used with scikit-learn had limitations to what you could use it with. For example, you couldn't use any watch lists or other things that I will mention afterwards. So you set the parameters that I will tell you about in a moment. You set the number of rounds, then train the model, have a predictions. Predictions are in form of an array, and in pandas, overwriting the whole part related to the template where there was these ones and zeros, you just provide that we don't want to use an index. So to anything other than index in our prediction, we just overwrite it with our array. And it will go element-wise and overwrite every piece in data frame. And I think it's very similar in R, when you want to assign vectors or matrices. And then we just save our submission to CSV. It's not something very good, but well, you can add more rounds, play with parameters, and do the proper validation. So I will not cover the validation here, but it's very often in Kaggle that you overfit the model because you too much focus on having it be good on the first part, which is called public leaderboard. And then you have a private leaderboard, and it turned out that actually not the algorithm, but you yourself overfitted the model. So it's not only algorithm that can be overfitted or biased, it's also you. So now I just give the code example to properly convert the feature, because get score gives you like F0, F1, F2, and so on. And normally you have feature names. Well, for this competition, it doesn't really make a difference. But for others, there have more meaning. So if you want to have names, you could use this code example. I just put it on paste bin, and you can copy paste it from there and test yourself. And I also gave you an example with how to use it in scikit-learn style. Very similar, almost 3/4 of the code are the same. So simply here you create the model that has the functions fit and predict probabilities, and these are the functions used in scikit-learn. And instead of using the dictionary, the parameters are in the construction of the class. So now a few words about parameters. So I have told you that XGBoost is gradient boosting plus a little bit the combination of random forest and bugging. And actually random forest is bugging, so combination of random forest and gradient boosting. And similarity with bugging is that you can take the subsample. So it's not anymore resampled, because you actually would have a fewer examples that you would learn on, but it provides you a similar advantage. So it helps you to reduce the variance And also, similarly, like in random forest, having a call sample on the tree level or each level of the certain tree helps you to decorrelate with errors that are coming from variance and reduce the variance even further. Depending how your feature space looks like, so for example, if you have a lot of features that are correlated with each other, it may turn out that your best choice for this would be 0.1.
So we have 5 up to 10 minutes. We have to let this.
Okay, let's go with up to 10. Okay, so you can also take 0.9 because sometimes you may lose information if you take too small sample of the columns. Especially for the columns, it's relevant. For the examples, it depends how many examples you have. And now, the ETA is the shrinkage that I told you about, so you don't want to make too big steps. You want to just go a little bit, see around where should you go, and then go a little bit, and go a little bit, and so on. Then you have a maximum depth, which is pretty straightforward, so how many levels your tree the maximum would have. And of course, if you choose too many levels, you are overfit. So you don't want to do that because your score will be very poor. But sometimes you cannot also capture the complexity of the model if your tree is too small. So there are other regularization parameters, first of which is the minimum child weight. And in this particular case, it's the value of the Hessian. So for regression, the second derivative of the squared function is just 1. So each example has value equals to 1. For classification, it's different. And actually, there was some math trick that was done that logistic regression doesn't use exactly the derivative of logistic loss function, but something else. And it's simply 1 minus predicted probability times predicted probability. It's your weight of the child. So maximum it would be 0.25, not 1. So it very much would depend on what problem you have. In regression it will be straightforward and it will always depend on the number of examples. In classification, the examples that you are not sure about will have a higher weight. So it also kind of makes sense. And this is the thing that totally differs XGBoost from other gradient boosting machine methods. And it's called regularization. So in regression, in linear regression, in order to simplify the model, you have either lasso regression or ridge regression. And it's simply, in addition to the model that you normally have in regression, you also add a penalty for your loss function that is either an average of the weights that are assigned to certain values or a squared average or root from squared average. And it is done exactly the same for the objective function originally defined in XGBoost. Then there is some math magic that is not easy to capture because there is not yet paper published for it. There is just some article that the guy really makes terrific math transformations that are not so easy to follow. But it ends up like this for the tree structure. And simply your gamma would be 3 in this case, and your lambda, it is not that intuitive how it affects the model, but in original formulation, it is simply multiplier of the out to norm. So similar thing like in ridge regression. So some cool things that XGBoost has, and I haven't seen in other things. Maybe I just don't know that they are there. And watch list normally is used in neural networks to prevent overfitting. So if your training error goes down and down and down and down, and normally you have a split in train and test set, you make another split to have a validation set. A small set that in each round of boosting is also evaluated, and you can see that when the training error goes down, and then your validation score starts to go up, it means that in this very moment you start to overfit, and it's time to stop. Because finding the appropriate number of rounds in boosting is not very easy task, and using the watch list very much helps. Another thing is warm starts. So imagine that you have some model and you would like to improve it. Like I gave the example with this BMI. So normally you start with this average or something very simple, but you can start with any model and simply iterate from that. And last but not least, I think it's quite new development, at least in Python. I haven't seen it in earlier version. You can limit the number of rounds, so it's very easy, but it was really useful. So you can train your model, for example, on 500 rounds, but then on prediction is only 100. But on another prediction, 200, and so on. And you can, when you make a hyperparameter tuning, then you can simply train one model and then apply it many times with different parameters, and it will be much faster than training again and again and doing actually the same thing. So, last but not least, about our competition is, I told you that XGBoost is an algorithm that wins every competition. So who won that? The competition that I presented. So in Rossmann, it was all about feature engineering, but the final model was 20 XGBoost models. So it's funny times, because when I was studying, a single model was a one decision tree, and an ensemble model was, for example, boosting or bugging of these trees. Today, single model, they call 500 rounds of XGBoost. It's the single model. And then you have 20 such algorithms, and it's your ensemble. Similar was with Avito, but the total overkill is with Autogroup. So they created 33 models, some k-nearest neighbors, naive Bayes, different decision trees, added some 8 features, then they trained it on few hundred, I think, models of XGBoost, few hundred models of neural networks in Lausanne framework, and then adaptive boosting with some extra trees, which is a super fast tree building algorithm. And then as a third aggregation of the model, they aggregated in this way. And normally you could say that it's crazy and it's probably just a strike of luck that someone wins data science competitions. But actually, this guy was a top one Kagler for some time, and the other one is just in top 10. So they consistently either win or are in a very top of couple of thousand teams that contest in it. So it may look ridiculous, but it's well validated. Normally it's internally validated, and then the best model is chosen, because in Kaggle you can choose 2 models to submit, and the best one is chosen. So if you'd like to make an even deeper dive, then if you start your
Sorry about that. If you want to make an even deeper dive, we have the presentation online on our meetup. We have to get going. Sorry about that. And we have the competition to go. Awesome presentation. Thank you very much.